I'm quite scared to realize it's been 20 years since in this room I came in as an incoming graduate student, and I think Kip was one of the welcoming professors here, together with, I think...
I'd already been here for 30 years.
All right. Let's see. So what I'm going to try to do in the next couple of hours, I was kidding.
Tell that to Mark Kaminkowski, who's going to come in.
Okay. Is how we're organizing our thoughts and efforts within the LIGO scientific collaboration and what is now the enlarged community of gravitational wave experimenters and researchers with the LIGO collaboration in guiding our thoughts and work, as I said, for following up detection candidates, outstanding events that the instruments might record. And this is around the topic that I'm going to be talking about today, namely the detection confidence and how we're going to be building it in searches for gravitational wave transients. Here I put a slide to reflect my high-energy physics background, starting with a canonical counting experiment. Of course, in physics, high-energy physics, gravitational wave physics as well, we typically produce lots of data, not necessarily all meaningful and decipherable, but at least either using hardware triggers or using offline analysis methods, we can construct events that carry some information about what we're recording. And then we put them through some black boxes, sometimes simple, sometimes not so simple, that are called data analysis boxes, analysis cuts. And the outcome of that process is either you have a function of the world that gives you 1 if whatever you recorded was a signal, gives you 0 if it was not a signal, you discard that event. And so you end up with, well, that is part of the measuring of the signal you're after. And then you try to predict also the background. Okay? You try to predict the background, and then you put them on some plot that shows events, shows probability. You have the background, you have the foreground, and then maybe in that experiment you had 100 events background, you have a sigma of 10. You ask the probability of observing any events greater or equal of what you measured, given the background B that you predicted. And then you set the threshold on that probability, threshold A, in order to claim a detection. The question that we're posing here, and of course in LIGO and in every experiment, is if this is the end game. Well, we're talking about confidence, and although we're physicists, we're scientists, we should have a formula, we should have an expression that's going to give us what that confidence is all about. Sometimes it boils down to something that is just a feeling. The feeling of being sure or certain of a factor or issue. And the question here is whether that assurance, that feeling of confidence can come just from that number P. As I think I'm going to show you, this cannot be the end game for gravitational wave physics. Because first of all, the probability P tells us what is the probability of claiming a detection in the absence of the true signal. And this can be as low as you want. It can be 10 to the minus 5, 10 to the minus 7. But that assumes that we know the background perfectly. And moreover, there is also an arbitrary thing here. How do you draw, where do you draw the line of what that P should be? But ultimately, a detection has to be accompanied by physical interpretation. And this is where the instruments stop being counting devices and they become physics devices. An event is going to have parameters, it's going to have some characteristics, and the instruments, besides measuring the vector x, it also measures the probability of x given our model. There are parameterization of the model, and the probability of observing x assuming that model theta. And so the counting goes beyond that, and we need to perform parameter estimation, namely estimate the values of one of those parameters, theta, of the source, if unknown or poorly known, or do a hypothesis testing, namely decide if theta sub I is consistent with the known parameters from the theory. And so confidence in a detection may not come only from a simply low probability P. of course, I spent quite a number of years after another impossible experiment, and that is to establish whether there is a signature of a magnetic monopole in nature. And so, as I was preparing for this talk this weekend, I dug out some papers, and luckily now PRD has everything online, so that made my life much easier. And I went back to '82, and this is the first results from a superconductive detector for moving magnetic monopoles, Blas Cabrera, Stanford University. A single candidate event concludes, it does not conclude because I have hidden something here. A single candidate event consistent with one Dirac unit of magnetic charge has been detected during 5 runs totaling 151 days. And here is the infamous step in the superconducting loop capturing the flux expected for a monopole of the Dirac charge G. You could see some wiggling here, something that corresponding to liquid nitrogen transfer. So I was actually very much surprised to find out that Cabrera, in his '82 paper, had the detection checklist. In his paper was going through a number of instrumental issues.
You've been teaching physics 1, but
Yes.
very loud. You don't have to be so loud.
Okay. Sorry. Okay.
800 students?
800 students. All right. All right. So Cabrera actually went through a very interesting exercise of checking the calibration, the response of his detector. Checking line voltage fluctuation. There's a section in his paper discussing that. RF interference. Are we surprised? External magnetic fields. Ferromagnetic contamination. A bunch of other things. Spontaneous internal stress release mechanism. And then embarked in concluding on the physical interpretation of what the event that might be. Namely, of course, the flux is consistent with one Dirac unit. Cabrera thought that was conducting a zero background experiment. And started putting together the known physics behind that. Namely, what is the solar, what is the density that could made up dark matter that could be made up of magnetic monopoles of a given mass, some galactic velocity over here, and he ended up with an expected event of 1.5 events per year through his detector. I'm actually going to be using that. I'm going to be going back and forth a little bit to see similarities of the thinking, at least, that goes into this process. But let me change gears and go to, actually, to what is our main discussion for today, which is, of course, gravitational wave detectors. I shouldn't be saying much more than a slide here. We have those beautiful instruments, 3 in the US, 1 and 2 in Europe, using kilometer scale interferometer to detect gravitational waves. And they have recently completed a very successful science run, the S5, science run 5 for the LSC, the LIGO and GEO instruments, 2 calendar years through the end of September of 2007, and VSR1 for the Virgo, our Virgo colleagues, the last 5 or 6 months of the run. Analysis of the data is well underway, and what I think is a point of departure of those analyses is what is the basic notion of detection. And the basic notion of detection that's probably reflected also in the design of the instrument was coincidence here, something that actually that was not there in Cabrera's event. Cabrera had just a single superconducting loop, which is basically a multi-site information that is going to increase the confidence and is going to allow the properties of the wave and of its sources to be measured. I don't want to exclude beforehand that we're not going to be entertaining cases where a single instrument, maybe in coincidence with another electromagnetic observatory, might see something, but that is going to be our point of departure. The canonical tableau of sources has continuous sources and has transient sources separated in the, that 2x2 matrix where we have waves coming from the before, during, and after the merger of 2 binary neutron stars or black holes, or arbitrary transients corresponding to supernova or other not yet known processes that can be either all sky or triggered by electromagnetic events. We have sinusoidally signals with modulation corresponding to the corresponding of the electromagnetic pulsars, and of course persistent stochastic radiation of astrophysical or cosmological source origin. And so here we have that right-hand side that corresponds to the short duration events, something that we're going to generically refer to as transients, that we're going to be talking more today. So starting off with the in-spirals, the search here is to look for something that may be up to from 100 milliseconds out to tens of second signals corresponding to the final spiral of the binary neutron stars and potentially a binary black hole. This is a system that is well understood for gravitational detectors, and waveforms are known, something that allows us to use optimal match filtering for them. Of course, the goal here is to detect or place upper limits on the rate of compact binary coalescences, and of course measure or constrain properties of the population. Of course, in the process, you probe the binary system merger, and of course, you have the ability to do beautiful tests of gravity. The methodology here reflects exactly that statement of the knowledge of the waveform. Namely, you start with a template back, thousands of such waveforms covering the parameter space of the entire signal. That is filtered. You create the output of the match filter as a time series, which you threshold, and you create triggers. So this is the corresponding hardware trigger in a high-energy physics experiment. The trigger that identifies the template and the coalescence time of the binary that you then bring in a coincidence module. Namely, you use that information from multiple detectors and you form coincidences to further reject the background and have a higher ability to distinguish a detection. Then it is where you plug in consistency checks for the data, and this is one of the tests that we're using actually. That's actually a cartoon, or actually of what actually coming out of the instrument as a function of time, the output of the optimal match filtering, and the signal to noise you threshold at some value, and you identify the triggers. And the CaJAGWR test is something that you use in order to measure the goodness of it, to measure how well signal to noise, if the signal to noise accumulates as you expect for the template. And then, of course, the triggers and in multiple differentiators will have to have consistent signal parameters. Here, I'm going to use the punchline of such a search. And this is from our most recent publication on the S3 and S4 searches for binary neutron star black holes. Roughly 60 days of lifetime, reached at the level of 70 megaparsecs for optimally positioned binary neutron stars, and for binary black holes out to tens of megaparsecs. Here, what you plot is the cumulative rate of events, and this is what is on the y-axis, as a function of your detection statistic, of the combined SNR. And here you see in blue the rate of events as obtained in the so-called zero-lag coincidence, namely where the data are not time-shifted. And then when you see what you see in red stars is the average background obtained from time-shifting the data between the two sides. And we see the variance on that measurement. In that search, for example, if you were to choose a threshold of rho squared of 80, you could see that you would have one event. That would have been your one candidate. You could see what would have been your expected background. And of course, in a while, we're going to be making statements about the probability about this event. But however, this search performs a search without any threshold, simply looks at that distribution and examines that loudest event that remains in that distribution. Shifting gears a little bit and moving to bursts. I have to be done by 5. Okay, so okay, fine. This is a search for transients that may last from a few milliseconds and now up to a few seconds, that have in the frequency regime of 100 hertz out to a few kilohertz. And the important thing is that they're not tied up on a specific source or waveform. This is what characterizes, and they can be performed in an all-sky blind way, or they can be actually targeted around the time and, of course, direction of electromagnetic triggers like GRBs, X-ray glitches, optical transients, and the rest. Here, our goal is, of course, the direct detection of such astrophysical sources like core collapse or the merging phase of binary systems, or any stabilities or exotic things like cosmic string cups and kinks, or otherwise establish upper limits on their flux or limit the amount of energy that is emitted into gravitational waves. The methodology I'm going to be discussing a little bit more in a second uses time frequency methods along the lines of excess power, of course involving coincidence and cross correlation, and there's going to be more coming up in the next slides. But a part of the methodology is actually working together with the spiral groups in order to pursue the full evolution of binary compact stars, since their spiralized phase is going to be through the merger and rig down are also going to be picked up, are going to be burst-like events. Talking a little bit more on how the burst search proceeds in a nutshell, you're basically projecting the data onto a basis. It could be a Fourier basis or it could be a wavelet basis. Here's the time frequency plane of instrument 1. Here's the time frequency plane of instrument 2. You normalize the noise. You threshold pixels. You find the long pixels. And then you form clusters of such pixels. And then you require coincidence between the two instruments, both time-wise and frequency-wise. You may as well select your signal to fall within a given frequency range. So here, for example, it could be from 100 to the 1 kilohertz or 2 kilohertz range. And this is the basic event selection for burst-like events. The essential part here, which I'm introducing now in more detail, I didn't have a chance to do that for the in-spiral search, is to repeat that experiment by shifting the data, the timestamps of one instrument with respect to the other, and do that, let's say, 100 times. And so you perform what you think are 100 independent experiments, and 100 times of the opportunity to measure what is the rate of coincidence, which you know cannot be astrophysical. We're going to discuss on what conditions this is going to be true in a second. And so here on the x-axis, you have the time slide, slide between the two instruments in seconds. And here you have the measured rate. You can have the mean, and you can have the RMS, and it's going to give you a measurement of your accidentals. This also gives you an opportunity to tune the search in an unbiased way. Namely, any thresholds you decide based on time-shifted data, you know they cannot be reflecting any bias from the fact that, hey, maybe you have a signal that you're trying to extract on purpose here. And then you set the threshold in this process to the number of accidentals you expect, and you proceed with your search. This is not only the only elements, though, in a search, both for in-spiral and burst searches, namely transient searches. Data quality and visitors are of paramount importance. Things that we're after is high seismic noise, for example, or wind or overflying jets. There could be calibration line dropouts. It happens and may create a signal in the dark port. Or, for example, the very end of a segment, the instruments become, namely of the science segments, may become noisy. At the level of the signal itself, we're using consistency checks. We're using, for example, for the two collocated Hanford detectors, the H, the reconstructed H, has to be consistent among them. And moreover, even if we don't know the exact waveform, we can use the waveform of one instrument as a template for the other instrument, and we can create the cross correlation and use that as a measure of the consistency between the two sites. Of course, you expect random noise to be uncorrelated. You expect for nearly aligned detectors this to be highly correlated. The end result here is coincidence events, just like in the spiral search, that are characterized by a significance. We're going to be talking about that in a second. They're characterized by time, frequency information, amplitude, waveform similarity, if this we consider to be a waveform similarity coefficient. And you do that both for the zero-lag events, namely where astrophysical signal may be present, and you do that for time-delayed coincidence between the sites where we know that astrophysical signal cannot be present. So what we have at the end of the day? At the end of the day, we can have plots like that, where we have on one axis the measure of the correlation between the two sites. On the other axis, we can have the measure of the excess power in every event. And you can superimpose onto it time-shifted events. Here they're in solid black. And we can superimpose on it coincidences, namely zero-lag events, and these are in a light gray. And from the tuning process using only background, you set thresholds into that. It could be horizontal for no good reason. It could have been also diagonal if you wish. It is a matter of quasi-ad hoc choices at that level. And you identify signal as a possible potential candidate, something that's going to fall beyond your expectations from the background. If you project now, for example, if you take one projection on the y-axis here, here you measure the coefficient here of the cross correlation between the two sides, and you could see in solid histogram the background with 1 sigma shaded regions, and you can see that the threshold of 4 you've imposed here in this search that we've recently published allowed no remaining event. That's how we're looking for transient sources. Now, is there need for follow-up in gravitational wave counting experiments? Well, here you could see that at least for one of the searches, you could see an almost arbitrary threshold. I mean, where do you draw the line of what that false detection probability is going to be? It's going to be 0.01, 0.001. You don't know. In most cases, detection and upper limits proceed in parallel. We set upper limits, and then we follow up candidates. And so one may say, well, why don't we use the Feldman-Cousins method? Namely, you set upper limits at the 90% confidence level, and if they exclude the zero flux, they can provide you the detection. Well, but these are 90% confidence level, and probably for a detection confidence, you need something much higher. Instruments are also very complex. There are thousands of channels. It's almost impossible to fold upstream, namely upstream, before opening the zero luck box, before looking at your astrophysical, at the data that might have an astrophysical signal. It is impossible to do that, to fold upstream every single bit of information in that function f of x. Even if not leading to a detection, a follow-up may lead to understanding detector systematics and overall instrument diagnostics. It has high value from that point of view. And this is where it boils down to some comprehensive list of tests a candidate will have to withstand and will allow us to assess our confidence as to whether it is a detection candidate or not. And this is where we get now to the detection checklist.
Last quick question. Searches can operate at a fairly high false detection probability or a relatively low one. If you have 100 time slides, can you have a false detection can you evaluate the false detection probability
exactly
smaller than 0.01?
Exactly. No. So that means that
set a threshold below that.
Absolutely. Yeah. Yeah. You're going to need 1,000 time slides or 10,000 time slides if you're going to go lower. It gets into other problems. Gets to these problems. Or not yet. All right. A couple more things that's worth putting on the table here. And this is blind analysis versus a posteriori event inspection. Upper limit searches are performed in a blind way. Namely, we don't, rather we look at time-slighted data or a small fraction of in-time data that we use to define all the selection cuts. And usually in the process, we balance the false alarm rate with the detection efficiency. What is important is that analysis to fix before opening that signal region all the analysis cuts. Okay? And this is a process that is going to guarantee the claimed coverage of your upper limit result. Now, a posteriori event inspection does not contradict that blind analysis, upper limit setting at least, as long as the blind selection of events is not revisited in order to reflect the findings of an a posteriori inspection. However, the a posteriori event inspection, when it comes to establishing detection confidence, does fold the biases of each one of us, reflecting our priors. So, on the road to detection, that assessment of confidence, almost like in Cabrera's paper, and has those instrumental aspects that are going to be investigated, and the phenomenology, what is the physics that event might have that are being investigated. The instrumental aspects go from the statistical significance to the environmental and endothermometric vetoes, issues on the detector status and data integrity, aspects of calibration errors, scrutinizing event, the very event, and looking at a multi-instrument response, and of course looking at multiple analysis methods and what they may bring us. Whereas this is where probably the line is blurred, where the extraction of the waveform and a source model that's associated with that information from electromagnetic counterparts, directional analysis, distribution analysis, and Bayesian analysis that may all bring into play to help assessing that confidence. So I'm going to try to go through most of them in the remaining of this talk. Starting with the statistical significance. Namely, we need to have a reliable estimate of the background. Namely, the number of the chance coincidences that our measurement has. And there are statistical and systematic errors in the background. Of course, ideally, one should switch all gravitational wave sources and repeat the measurement, which is, of course, not an option. However, it is reasonable to assume that the two gravitational wave events are only a negligible part of the event sample. Moreover, the time slides, the time shifting operation of one detector with respect to the other, there is a crucial question whether that is creating independent data sets. The answer is yes, if the system is ergodic. If the time strides are longer than the maximum coincidence window, and if there are no autocorrelated up to the maximum time shift, if the single detector event lists are not autocorrelated up to the maximum time shift. So everything then boils down to assessing, for example, if the measurements out of 100, 1,000, whatever the number of time slide is, does indeed follow Poissonianity by assuming that we're trying to measure the true background rate nu. And we're doing that in 100 experiments. It's one yielding a measurement n. That we can check whether it fits the Poissonianity. We have actually done that. And I'm extracting here a plot from our 2005 Burst search, where we're actually, for every measurement of the background, the accidentals here, we're actually projecting them in a histogram, and we fit them to a Poisson process. However, the detection candidate will have to extend questions of the background, systematics. For example, here, that reflects one choice of stride, namely by how much you move data of instrument A with respect to data of instrument B. Is it as robust against different strides? If you change the 3 seconds to 5, or square root of 17, or you pick a collection of 100 random numbers and you time shift the data, is the number, the mean, is these numbers used from time shift consistent? Moreover, is the ergodicity hypothesis holding? And there's always a back-of-the-envelope calculation. Namely, for background, you can use the singles rate from each of the instruments. You can use your coincidence window. You can come up with an estimate of what is your expected coincidences. These are the kind of things that need to be addressed. And at the end of the day, you have to quote a systematic in that measurement of the background. We think we know the background, probably at that level of systematics. But these are the questions, though, that need to be addressed, because it's going to make a huge difference if it is a 0.1 event or 0.01 event or one event, the systematic in the background of the process we're measuring. Moving on to environmental and interferometric vectors. As you know, the instruments, gravitational instruments, record thousands of channels that record the environment as well as internal test points of the interferometry. Now, the searches generally fold a priori, namely before looking at the signal region, what we think are smoking gun or debugged vectors based on information from environmental and interferometric channels. Namely, a set of conditions that under no circumstances we're going to allow ourselves to consider a detection when this happens. For example, here I saw a time series. This is in the antisymmetric port of the 4-kilometer Hanford instrument. This is actually a band pass from 70 to 100 something hertz, in order to show how that was actually correlated with the signal in the one of the microphones in the instrument. in a slightly different language here, we see how a line monitor, a voltage line monitor, depicting glitches in the lines, and how this is actually reflected in the antisymmetric port here. In the time frequency here, we see a quite significant glitch appearing in the instruments. So these are the smoking gun channels that were debugged and are used beforehand in a search. The way they are established is, I think, quite important. It's going to be coming back on the next slide, because you have to establish it both statistically, and you have to look at lots of glitches and see if there is significant correlation with the auxiliary channel and vice versa. And also by something that is the coupling mechanism that is going to take the coupling mechanism between the auxiliary channel and the dark port of the interferometer. Of course, when you talk about vetoes, the false dismissal probability is of paramount importance. And now going back to the a posteriori examination, there are many reasons for which an outlier event, namely that the one event, the loudest event in the spiral search, or maybe something that may be in the signal region of the burst search, that many reasons for which you have to go back and revisit the veto strategy. Well, as I've just argued, there are the number of channels that are available for establishing a data and veto and data quality conditions is huge. And not all of them are studied a priori. It is a formidable task. That has become even more formidable if you consider the phase space of parameters for a veto. You can consider the threshold, you can consider the time frequency volume, you consider tons of conditions, tons of parameters that come with each one of these channels that are impossible to exhaust all of that a priori. Moreover, any candidate signal may have specific morphology, either in the time frequency plane or some other aspect for which you need to look for specific veto analysis that it might require. Now, I think there will always be something, quote unquote, in the detector's auxiliary channels that may hint a correlation with the instrument's environment or interferometer. However, I think it is impossible to make any conclusion just from a single event. You need to quantify, and you need to proceed with accepting a post-facto veto. We need to make sure that it has a false dismissal probability. And moreover, the veto amplitude has to match expectations from known or measured couplings. One of the success, for example, of the sample events that I've shown either in the microphones or in the line monitors is the fact that the measurement in the dark port is consistent with the size of the glitch that you observe in the microphone or in the line monitor and the transfer fraction that has been measured. After examination, you may proceed not to accept a post-facto veto if that has a very high false dismissal probability, or you take the measured amplitude of the auxiliary, the veto channel, and you show that the expected signal in the dark port is much less than the one that is measured, that is seen. Of course, it leaves an open question of how you establish that there is a statistical significant veto. Here I have only an example of one method where you can do that. You can, like time-shifting gravitational wave data between two sites, you can time-shift gravitational wave data with veto data, and you can see whether, whenever they are right on top of each other, you see, for example, the fraction of events veto to be statistically significant, the excess of vetoes that you observe, respect to pure chance that is measured by any random slide between the data. There are other veto considerations that need to come into play. Again, and not all of them easily quantifiable. Okay, you have not seen anything in the magnetometers. You have not seen anything in the line monitors. We have to demonstrate that the auxiliary channels were indeed functioning properly at the time of a candidate detection. This is something that we have to undertake. And moreover, we can look for environmental disturbances that might have been missed or are unclear in the local environmental monitors. That might require going back and look at catalogs of earthquakes or information from power companies regarding known to them glitches, any switching on and off of major local equipment, and other considerations. Okay, I guess once you've gone through this, you probably, and let's say your candidate event passes successfully, you may say that, look, maybe there's something interesting in there. It never hurts to go back and do mostly a verification step of things that analysis, any good analysis, should be reflecting almost automatically. For example, we think we're analyzing data when we're only in observing mode of the instrument. So without, for example, any hardware injections that might be taking place. So we can always go back and look here as a function of time. Here is a plot of something that we call state vector. It tells us what is the state of the detector at any given moment. And so, for example, you could see that 4 is the science mode. You could see the time that you have a plausible candidate if indeed this is the case. The detector's online logbook has a wealth of information that is not easily put in a scannable way by machines. So it's always important to go back and check what the instrument's log was recording at the time of that event. Moreover, figures of merit that are used as part of the running of the instrument, they're not immediately folded in the offline analysis, but for example, they can tell us if we look in that plot as a function of time. You could see, for example, here, this is the spiral rates, a direct reflection of the noise in the instrument. You could see, for example, here, when the instrument is not in acquisition or is not in science modes, that goes down. You could see that mostly falling, mostly remaining stable and falling the science status of the instrument. However, you could see during that stretch of science mode, lasting a few hours over here, you could see the sensitivity drifting down to almost 0. And so, if you have something here, you can ask yourself, what was happening in the instrument was not picked up by my analysis in the first place, and we used that segment to analyze. Do we need to go back and revisit? Would we ever believe something that may happen when the instrument was misbehaving? Also, things that may be considered a little bit paranoia, namely going and checking if there has been any data corruption in the process. Data passes through multiple stages; they're reduced. Are, for example, the checksums between the various data products correct, or results between analysis performed with various levels of data consistent? These are the kind of things that, as I said, are a verification step when it comes to claiming something. And then it comes to calibration errors. We think we understand our calibration to a level better than 10%, both amplitude and phase. But could it be any fast fluctuation nearby of that event? Which means, again, going back and checking locally what was going on. Or we have various corrections and improvements when it comes to calibration constants. Is, for example, the event remaining when you use one version versus the other? Another aspect that I think is going to play a significant role is the presence, the use of hardware injections, for example, in nearby times, in order to tell us quite a bit about calibration errors in the most direct way. Hardware injections can play a role beyond that. They can tell us about any couplings between the auxiliary channels. So having hardware injections in nearby times is going to be able to address quite a number of crucial questions when it comes to detection candidates. And then we go to the very event itself. So we've seen that most of the rest of the information was reasonable or not. But if we get there, scrutinizing the event itself, here, for example, is a background in spiral figure from Livingston. And here at t equals 0, we see the output SNR of the MUTS filter. peaking and crossing the threshold. And you could see also this is the chi-squared, namely the goodness of fit, actually being quite good over here. You can see the dip here. The analysis discards obviously high chi-squared as glitches. And so this would have been, well, not would have been, it is one of the events that ends up in the background of the in-spiral cells. Going back and looking nearby, here are 2 seconds of the data, the output of the SNL, the output of the MATS filter, as well as the chi-squared. You could see what's going on in the instrument. You can see multiple triggers above the SNL threshold within hundreds of milliseconds away, and all of them being inconsistent with any template, all of them characteristic of noise. In other words, establishing that it was a very noisy interval at the time that this event was recorded. So the scrutiny, I think, at the end of the day, boils down to establishing how stationary the instruments are around that time, and addressing questions also along the lines of, for example, the analysis proceed with a given stride and with a given start time. How sensitive is that with respect to that? If you change the boundaries or the size of the analysis block, do the results change? And operations that happen, like the trigger clustering, for example, is that event sensitive to that clustering? And if we change the criteria, will the event be any different? Beyond the single detector, it is information from multiple detectors that is going to be cornerstone to how we're going to be proceeding. Events have to be consistent among instruments, both in the sense of the time, frequency, volume they span, the amplitude, and signal morphologies, superimposable. The most elegant way that this is quantifiable is through the means that fully coherent method provide us. Fully coherent method here is only a snapshot in the case of the 2 collocated detectors. Fully coherent method, as Grushel and Tito have shown 20 years ago, allows us to start with a linear combination of the data streams from all 3 detectors and parameterize that to the direction, namely with 2 numbers. And then they've shown that for the true direction of the gravitational wave, that linear combination can actually cancel the presence of the gravitational wave signal. In the case of the 2 detectors, this is quite straightforward. This is the subtraction of the 2 collocated detectors. And here you see how, for example, the coherent sum, namely the noise-weighted sum of the 2 Hanford detectors, in the case of hardware injections of 1.4 solar masses at 5 megaparsecs, you could see how actually it increases the SNR by 10%. And here in the null stream, namely where you expect to see no residual signal, you see pixels that are consistent with noise. So it is that fully coherent follow-up of the triggers, of the coincidence triggers, that is actually going to go beyond that. In the process, rather than picking the direction and minimizing, you can actually scan over the whole sky and extract the source location in this process. Whilst knowing the sky location, you can actually perform a best fit waveform. And so here is an example where a simulated waveform corresponding to a supernovae was injected at an SNR of 40, and this is underlined. You know, where we could see how the injected we could see the injected waveform, and in blue you see the extracted waveform H plus and H cross, which is actually consistent with noise here. The question to be asked is if the event was not registered in one of the detectors, if that was because it was not collecting any data, which would have been unfortunate, or if it was because it is not sensitive enough, or it was glitched at the time of the event, or you need to invoke special assumptions about the polarization of the source and, or the source direction in order to explain that. Multiple methods is part of living in LIGO. Namely, you have multiple methods that analyze the same data set for the same source. So the moment of a detection candidate, confidence may or may not be around comparing nodes among those methods. For example, is the significance of a candidate event comparable among them, or the extracted signal parameters are in agreement? This process generally increases our confidence against algorithmic or implementation mistakes when it comes to methods. However, something that should not be overlooked is the fact that this process of using multiple methods also increases the false alarm rate. So remember the trials factor. So you should not overdo it when it comes to using multiple methods, except in cases where actually methods work synergistically. And this is going back to the case of the in-spiral, merger, and ring down, where, for example, everyone would like to know if next to your best burst candidate you have something that may look like an in-spiral, and vice versa. So this is the kind of steps that reduce the false alarm rate and increase our confidence when they are complementary as opposed to merely overlapping. Moving on to what one can say about a detection candidate, much of that is going to be around the waveform extracted and any source that may be suggested. Well, that's reasonably well described for in-spirals and rig downs. However, it is quite a challenge for the rest of the sources. It is heavily dependent on the SNR. You've seen the cartoon of the waveform extraction for an SNR of 40. That would be a nice gift of nature of SNR 40. But that picture would have been very much different for an SNR of 8. Do we need to reanalyze events with refined waveforms, with refined templates? Could it be that the gravitational wave is somewhere in between our models that we search for? I think these are valid questions that we should be asking. Or if we extract any waveform, do we do a targeted search, a match filter search, using the waveform that was extracted? What may catalyze the first detection is, of course, an electromagnetic counterpart. The presence of any prime, and here by prime I mean something that is broadcasted in the GCN, something that goes out to the preprint archives within a week or so that happened. These are, of course, prompt and public, and they should be looked at. And they're going to be, of course, increasing our confidence in a spectacular way. However, I'm asking whether you should be looking at subprime ones, namely ones that that didn't make the threshold for a GCN, didn't make a threshold for a Astor PH preprint in a matter of days, and they're simply sitting on the hard drive of some satellite experiment. The direction that can be extracted from the coherent and incoherent methods, of course, should be confronted. We may ask if there are known sources overlapping the ring, or if it is a more limited patch on the sky corresponding to the direction of the candidate event. Identify astrophysical point source locations, or use the luminosity data to plot the cumulative luminosity per solid angle for varying depths. Namely, plot the DL10 d omega at various depths. For example, up to from 0 to 1 megaparsecs, out to 10 megaparsecs, and then to 100 megaparsecs, and see if your reconstructed ring or patch, what it interacts. At the end of the day, assuming that we have one loud event as a detection candidate, this implies that should be many more weaker events corresponding to a fundamental source population behind it. I'm going to be asking if we're going to be able to probe the spectrum of such population. Of course, in a fixed threshold counting experiment analysis, just like the burst search, for example, this isn't easy. You fix the threshold. And you need multiple analysis of continually decreasing thresholds down to 0. This is something that Alan referred to as the ladder-like analysis, or I forget the name. Is that ladder or step-like analysis that other experiments have performed, where you basically confront the distribution of foreground. If this is the distribution, I picked the strain here, of the foreground to the background, and you can use arguments whether the distribution might be consistent with one to another or not. This is another direction that Now, through this discussion and organization of thoughts and work, as I said, we have an interesting twist during the fifth science round of the LIGO scientific collaboration, which is a blind injection challenge. That was basically introduced in the second half of S5. Records of such injection are kept hidden from all, but only a handful of people. And the goal here is to test our detection establishing internal process end-to-end. Actually, come to think of it, it is an interesting insurance policy against leaks, both in the transmitting and receiving way. But anyways, in the process, we have decided that we're going to have N burst and inspiral-like events injected into the LIGO instruments during S5, with N equals 0 also being a possibility. We expect that to become routine in S6 and beyond, or at least until nature provides real astronomical events routinely. So back to the monopole paradigm, I think you might be asking, what did I hide behind that box from Cabrera's 82 paper? These data set up an upper limit. Cabrera chose to set an upper limit. The event did not pass his detection list. In the process of digging in the history of that, I found out what Luis Alvarez commented on the Buford Prize claim on the discovery of the magnetic monopole in 1975. Remember, it is 1982. This is 7 years later. Not far from where Luis Alvarez and Price were discussing Price's 75 claim. So Luis Alvarez said, my immediate reaction was to say congratulations. But within a moment after Buford left my office, I started to make some calculations, and I soon convinced myself that the experiment of Price et al. Was in serious conflict with several others, including our own sheds in moon rocks. Well, what I think we're reading from here is, of course, the confidence of a detection can come from its consistency with all past and future results. Of course, for LIGO and gravitational wave physics, that might be easy. The improvement in sensitivity is spectacular of the instruments. However, let me throw here an example. One should be skeptical if LIGO sees in S5 events with strength and rate that should be detected in S5, in S4. And you can go with +1 through this loop. But I think here what we see is that the ultimate juror of a detection is in the next generation an improved detector. Oops. And see, this is actually what Cabrera did. He spent 10 years of his life, he worked with several guys over in IBM, to come up with a detector that is 3 orders of magnitude better. Of course, Cabrera's experiment, the next generation experiment, never discovered anything. And so in his conclusion of the 91 PRD, Cabrera goes and says that his 82 event, the Valentine's event of 82, should be discarded. So I'm concluding, mostly reflecting my own thoughts and take here, so you should not hold the LIGO collaboration or wherever responsible for these statements. I think the debate for the confidence of the first detection may be never ending. For certain types of events, and I have a disclaimer of no-brainer detection, we can discuss after that what, for each one of us, constitutes a no-brainer detection. As arguments challenging the particularities may be brought up both from the instrument and interpretation perspectives. The particularities, right? For this, the ultimate detection confidence for the first detection may have to be provided by the second detection. And again, sticking with the monopole history, I'm quoting one of Caltech's professors, John Preskill, concluding his 84 review article on monopoles. As of this writing, John was writing, it is not certain that nobody had seen one. What seems certain is that nobody has seen two. And I'm going to conclude here by summarizing that the LIGO scientific collaboration is making constant progress towards methods and criteria for the first detection and its interpretation. Joint analysis with LIGO, present, by present means that the data we have already collected and we're analyzing in future as the two instruments are going to be planning together in the immediate future, will improve our ability to make detection. Detection lists help organize our thoughts and our work. There are live documents. Totally blind or self-imposed detections and follow-ups of search outliers hone such procedures, mature our thinking, and test our sociology. Establish confidence on the first detection candidate will be an exciting moment, of course, for collaboration and the whole field, I think. But it won't necessarily be automatic or straightforward. And my fear is, of course, a detection right at the threshold. That particularities, that when you sift one sample on your pipeline and you see slightly different things but consistent, and candidates without a source and without a waveform, quote unquote. That of course goes back to the threshold. Something at the threshold is not going to have the spectacular waveform extraction that we've seen in the previous experiment. We should not forget, though, that while the first detection is a milestone, it is not our goal. It is only the beginning of course, the road to gravitational astronomy. And I hope you'll agree that it is a good time to be optimistic. The S5 analyses are well underway, with enhanced detectors, with many people in this room putting all their efforts to bring them online in less than a year and increasing our science rates by a factor of 10, if not more. And of course, the advanced LIGO that is going to bring detections near certainty. Remember, detection checklist and confidence is an active process. It's an active document. And so please do let us know if you think that there are other things that we should be testing. And please stay tuned. I'm done.